what are the likely questions that come out in the physics WAEC exam. So I'm going to do a revision, and then I'll be taking certain topics. In fact, I'll be giving you the formulas, the equations that you come across or that you use to answer questions in about 10 topics today. And I'm giving you the shortcut, so do not miss it. All right, do not miss it. I'm going to be giving you questions on motion, on projectiles, expansivity, on Hooke's law, elasticity, and the rest as we continue. So come with me. Third topic I'll be talking about is very, very certain. You cannot escape it in the exam. It will definitely come out. So make sure you stick around to the very end of this video. I can assure you, you will not regret it. Okay? Now let's start with the first one, which is the equation of motion. Equation of motion. So for your equation of motion, a quick revision. And what are the equations you have? Number one, equation of motion. All right. So first you have V equals U plus AT. V squared equals to U squared plus 2AS. You have S equals to UT plus half AT squared. Then you have S equals to V plus U over 2 into bracket T. Right? So these are four basic. Then you can also have your velocity is distance over time. Okay, velocity is distance over time. Now, we can also derive, these are for linear motion, though, equation of linear motion of a motion on a straight line. But when you are talking about vertical motion, motion under gravity, so I'm going to be adding 3 more equations to this. To derive the motion under gravity, all I need to do is to, anywhere I see A, I change it to G. And that is the acceleration due to gravity. Wherever you see S, change it to H. That is the height. All right. And for this particular equation, so the first one, my V is going to be U plus GT. Then I'm going to have V squared equals to U squared plus 2GS. This S becomes 2GH. Okay. Then you can have S equals to H equals to, all right, UT plus half GT squared. Now take note, this G is an acceleration due to gravity, and you remember that the force that pulls an object that is thrown up, that pulls it down, is the force of gravity. So that means the force of gravity is acting downwards. Okay. So when an object is falling, maybe a fruit that falls from the tree downwards, it's acting under the force of gravity in the positive. So the force of gravity is positive. But when you are moving in the opposite direction, you are throwing an object up, then you are moving against the force of gravity, and your G is going to be negative. All right. So that is that about that. Let's go forward. Moving forward, we go to the next topic that I'll be talking about, which is projectile. Projectiles. For projectiles, I will be talking about 4 basic formula. That is, the first one is time to reach maximum height. The time to reach maximum height, small t, is giving us U sine theta over G. I'm going to show you a shortcut and certain keys that you can use to remember this very shortly. Then there is time of flight. Time of flight is the time that it takes an object that is launched into space to return back to the horizontal surface from which it was launched. While time to reach maximum height is the time it takes to reach the maximum height. So this is an example of a projectile has this, is the motion in this form. All right. When you have an object launched into space at an initial velocity, and then it makes an angle with the horizontal. All right, launched, it goes in this parabolic form. That is a projectile. So the time it takes it to go up and return down to this point, that is what you call the time of flight. But the time it takes to get to this maximum height, all right, is what you call your small t. So you have the small t, and the time to return back is also t. So if the total time taken from when it was displaced or launched into air and when it lands is t plus t, that is 2t. So there's a relationship between your capital T, which is time of flight, and small t, 2t. So the capital T is 2t. So the time of flight, which is capital T, is equals to 2u sine theta over g. 2 of this, that's 2u sine theta over g. The next one I'll be talking about is the range. The range is simply the horizontal distance from where the object was launched to where it landed. This horizontal distance covered is the range. So the formula for range is u squared sine 2 theta over g. Please look at it. U squared, not u2. U squared sine 2 theta, not sine squared theta. Sine 2 theta over g. That is your range. And note that your sine 2 theta is the same thing as 2 sine theta cos theta. All right. 2 sine theta cos theta. So there are some questions that will require you to use, instead of u squared sine 2 theta, it will be u squared 2 sine theta cos theta. Right? And you can also calculate your range. Your range is the distance in the horizontal direction. So from this equation, if I want to calculate this distance, I'm going to cross multiply this. So I'm going to have my distance is equal to velocity times time. So this range can also be calculated. This S is the range. Our V, the velocity there, is now going to be the horizontal component of the velocity. So here my range can also be, all right, in place of this velocity, it will be u cos theta. U cos theta is the horizontal component times t. Okay, and that t is the time of flight. To move from here and land here, that is the time of flight it covers. All right, so capital T. So this can also be the formula for your range, which is u cos theta times the time of flight. All right, and the last is the t. If you want to calculate the maximum height, it's given as u squared sine squared theta over 2g. U squared, can you see this is not sine 2 theta, sine squared theta. U squared sine squared theta over 2g. Now look at this. If you look at all of these 4 equations, this equation 1, how many times can you see 2 here? U sine theta over g, there is no 2 here. Here, how many times can you see 2? 2 is appearing once. Here, how many times can you see 2? You can see 1, 2. 2 is appearing twice here. And then, so let me put these notes in a bracket. Of course, the last one, maximum height, how many times are you seeing 2? 1, 2, 3. 3 times. What does that suggest to you? The first thing you need to know that under equations of projectile, there are 4 basic equations, but out of that 4, there is one of them that lacks 2, does not have 2 at all. There is another one that has only 2 appearing once. There's another one that has 2 appearing twice. There's another one that has 2 appearing 3 times. That is another thing put in your pocket. The next thing is that one that has 3 or that has 2 appearing the maximum number of times. I'm talking about maximum height. That has the maximum amount of 2, which is what 2 is appearing 3 times. That is the maximum height. So you always know that maximum height has the maximum number of 2's, which is 1, 2, 3. And that is that. So that is equation on projectiles. Let's move forward. We're going to the next topic. Talking about work, energy, and power. What are the formulas you need to take note of on the work, energy, and power? Now for work, energy, and power, let's start by doing certain definition. All right, so what is energy? Energy is the ability to do work or the capacity to do work. So when you say energy is the capacity or the ability to do work, invariably or indirectly it means energy is equals to work done. So energy and work done, they have the same SI unit, which you're going to see very shortly. So let's quickly see certain so this energy, mechanical energy, okay, can be of two types. You have the kinetic energy and the potential energy. So for potential energy, mgh is mass times acceleration due to gravity times height, all right? While work done, you can define work done as work is done when force is applied to move a body, all right, from a point to another over a distance. So when a body is moved by an external force over a distance, then work has been done. So the work done, the formula is force times distance. So if the formula of force is force times distance, you remember that your force is what? So force is mass times acceleration. So if force is mass times acceleration, I can also say F equals ME or mg when we are dealing with vertical movement, acceleration due to gravity. So if I come back here, my F is m times g or times a, then multiply by distance s. All right, and then can you see my mass, my acceleration g, my distance and height, they are the same. Therefore, potential energy and work done are the same. All right, so the SI unit for potential energy is in joules, and then the SI unit for work done is also in joules. Now force, the SI unit for force is Newton. The next one we talk about, let's talk about power. What is power? Power is the rate at which work is done. Is the rate of doing work or the rate at which work is done. So anytime you hear the word rate at which, it means a particular quantity divided by time or over time. So when we say power is the rate at which work is done, power simply means work done over time. And what's the work done? Okay, so our work done is same as energy, mgh, over time in seconds. Okay, seconds. So the SI unit is going to be what? Joules per second. That's work done over time. And there is also a fundamental SI unit for power, which is also equivalent, which is watts. Okay, watts. So you can measure your power in watts, in kilowatts, then you can also measure it in joules per second. Let's talk about, so we have discussed force, we have discussed power. Let's talk about pressure. The formula of pressure is force over area. So force per unit area. If you are asked to calculate pressure, it's force over area. When you are asked to calculate impulse, impulse is force times time. That's impulse, force times time. All right, that is I equals Ft. So if you're going to write the SI unit of impulse, is going to be Newton seconds, not Newton per seconds, but Newton seconds, force times time. Then your momentum is what? Is mass times velocity, And then what's the SI unit for your mass? Or your mass is in kilogram, right? Your velocity is meter per second. So if you compare this to your impulse, you see that it's the same thing. Why? Because your force, this force is mg, all right? Or yes, F equals mg times time, all right? But your mass is kilogram, all right? Acceleration is meter per second squared times second. Seconds we cancel this, so you have kilogram meter per second. So the SI unit of impulse and momentum are the same, kilogram meter per second. So what does that suggest to you? They are also the same. Impulse and momentum are the same. Potential energy and work done are the same. Now let's talk about moment of force. moment of force. If you are asked to calculate moment of force, it's the product of force and the perpendicular distance from the point of application of that force. So moment of force is force times distance. So if it is force times distance, then our force is mass times acceleration, then times distance. Mass is kilogram, acceleration is meter per second squared, times distance is in meters. So we are going to have kilogram meter squared per second squared. That's the SI unit. All right, that is the SI unit for moment of force. If you come over here, let's try to look for the SI unit of work done and potential energy. Mass is kilograms. All right, our acceleration due to gravity is meter per second squared, times our height is meter. So meter times meter, that's going to be kilogram meter squared per second squared. Can you see it's the same to kilogram meter squared per second squared? So let's check for work done. Work done, this joules is also equivalent to force is kilogram, that's mass, times acceleration is meter per second squared, multiplied by distance in meter. So if you multiply, it's going to be kilogram meter squared per second squared. So that means your work done, your potential energy, and the moment of force, they have the same derived units. So all their units are the same. All right. Let's look at a few others. So we spoke about potential energy, work done, force, power, pressure. So in terms of mechanics, this is work, energy, and power. But when we get to electricity, we'll also be talking about work, energy, and power under electricity. So let's continue with the revision. Now the next thing we talk about is fundamental quantities, derived quantities, SI units, and dimension. Now when we talk about fundamental quantities, fundamental simply means the basic, the foundational, right? The foundational quantities on which other quantities are built. So these fundamental quantities, they are independent. They do not depend on other quantities. All right. So example, your mass, your time, distance or length, okay? They are fundamental quantities. They are independent. Every other quantities are gotten from that. When you say derived quantities, they are dependent on the fundamental quantities. They cannot stand on their own. They are not independent. They are dependent. So it is derived. That's why the word derived comes from. They are derived from combination of two or more fundamental quantities. Example of derived quantities: velocity, acceleration, force. Just name it: energy, work done, power, pressure. Anything that entails you combining two fundamental quantities, then you're going to get the derived. Other examples of fundamental: your current is fundamental, or your temperature is fundamental. Now for SI unit, that's the standard unit for all of these. So I'm going to show you SI unit and dimension for all of these, for the fundamental and the derived. Okay, so let's look at it. The quantities, then the SI unit, then the dimension. We'll show you how to derive the dimension as well. So for the quantities, let's start with the fundamental mass. The SI unit of mass is kilogram. The symbol is kg. The dimension of mass is capital M. Take note, not small m, not kg, capital M. Then that is mass. Then let's talk about length or distance. All right, the SI unit is meters. That's small letter m, but the dimension is capital L. Then you have time. That's another fundamental. It's measured in seconds. That's the SI unit, seconds. But the dimension is capital T. Capital T. All right. Number 4, let's look at current. Electric current measured in amperes. All right. That's the amperes. That's the SI unit. The symbol could be I. I stands for current. Temperature. Temperature is measured in Kelvin. That's the SI unit, Kelvin. So you can put it K, the symbol, temperature. Now, let's look at some derived quantities. Velocity. Velocity is the SI units can be gotten from the formula. So velocity is rate of change of displacement or distance with time. So it is meter over seconds. So that means the SI unit is meter per seconds, or ms minus 1. So if I'm going to write the dimension, m is L per t, or LT minus 1. Now, acceleration. The SI unit, the formula is velocity over time. Velocity over time, that's rate of change of velocity with time. So that's meter per second divided by second. That is meter per second squared. So if you are going to write the dimension, to be LT minus 2, or L per t squared. Next, energy, potential energy. Potential energy is mgh. So if you are going to write the SI unit, mass is in kilogram, acceleration meter per second squared, times height is in meters. So that will be kilogram meter squared per second squared. But if you are going to write the dimension, it's going to be capital M. That is the dimension of mass. Then meter squared will be L squared T2 minus. That is potential energy. Let's look at number 9, work done. Work done is force times distance. So if it is force times distance, that's the formula. So let me write it here, force times distance. So if it's going to be force times distance, then the force is mass times acceleration, then times distance, okay? So the SI unit of mass is kilogram, acceleration is meter per second squared, times distance is meters. And that ends up as kilogram meter squared per second squared. While the dimension for kilogram is capital M, from distance is L squared T2 minus. So the dimension for work done and energy, they are the same. Let us continue. Let's talk about power. Power is the rate at which work is done. So it is work done over time. And work done is energy, and it's mgh. So I can say mgh over time. So mass is kilogram, acceleration is meter per second squared, times height is meter, then divided by time in seconds. So that would be kilogram meter squared, all right, per second squared, times 1 over seconds. That would be kilogram meter squared per seconds cubed raised to power 3, s squared times x. Now, if you're going to write the dimension of power, it's going to be capital M, L squared T minus 3. That's the dimension. Next, pressure. Pressure is force over area. Force is MA, mass times acceleration, over area is meter times meter. All right, meter times meter, that's meter squared. So that's kilogram meter per second squared that's kilogram meter per second squared, divided by meter squared over 1. So that's going to be kilogram meter per second squared times 1 over meter squared. And we cancel 1. So you are left with kilogram per meter per second squared. So if you are going to write this dimension, it's going to be capital M, L minus 1, T2 minus. I hope that is clear. Let's look at some more. Impulse. Impulse is force times time. So force is kilogram. You know, force is mass times acceleration. Then we have times time. So mass is kilogram. Acceleration is meter per second squared. Time is seconds. So seconds cancels 1. So you have kilogram meter per seconds, or kilogram ms minus 1. So if we are going to write the dimension to be capital M, LT minus 1. Number 14, momentum. Momentum is what? Mass times velocity. Now that mass times velocity, that means kilogram times meter per second. So it's kilogram meter per second. So dimension will be M L per T, or LT minus 1. So the same thing, momentum and impulse are the same. Let's add one more. Moment of force. Moment of force is product of force and distance. So here is force times distance. Force is mass times acceleration, then times distance. So it will be kilogram meter squared per second squared. So in dimension, it will be M L squared T2 minus. You can write it 2 minus or minus 2 is the same thing, right? Okay, so these are the ways to, or that is how to find the SI unit and the dimension of each of these. Now, mind you, anytime you see force, it could be Newton. So in the option, here they can put Newton, distance is meter, so Newton's meter. All right, Newton meter, that's another SI unit. That's the fundamental SI unit, Newton meter. All right, so it's equivalent to these, all right, and this the dimension. I hope that is clear. Moving forward, we're going to the next topic. Next topic I'll be talking about is expansivity. Expansivity is actually the ability of a material to increase in either length, in size, and area, in volume, as a result of increasing temperature. So there are 3 different types of expansivity I'm talking about. The first one is linear expansivity. So linear expansivity is simply the increase in length of a material as a result of increase in temperature. Increase in length of a material as a result of increase in temperature. The particulate nature of matter makes us to understand that matter is made up of particles, tiny particles which are constantly in motion. But when there is an increase in temperature around matter, all right, the kinetic energy of those particles that are in motion will increase. And then when the kinetic energy increases, the motion will be faster. The kinetic energy increases, the motion will be faster than the usual. Are you getting what I'm saying? And when that motion is faster, is increased now, it will bring about increase in the length of that material, which is what you call expansion, linear expansion. So the linear expansion is increase in length. So the formula for linear expansion, the symbol is alpha, and that alpha is change in length over original length times change in temperature. So what does that mean? It means our alpha is dl over L1 dt. These are simple ways to remember the formula. And then you can also write it as alpha equals to LT minus L1 over L1 dt. This dt can also be written as theta, which is change in temperature, where your L2 is the final or new length, final length or new length. L1 is the original length or initial original length. Then dt is change in temperature, which is giving us T2 minus T1. And your dl, delta L is change in length, which is equals to L2 minus L1. So this is a form of revision. So these are the formula for calculating linear expansivity. Now when we get to the second, which is area expansivity, which is also called superficial or area expansivity, the symbol is beta. The first thing you need to know is that there's a relationship between this beta and the alpha, and that relationship is this: your beta is 2 of alpha. That means that is area expansivity is 2 times linear expansivity. So the formula, our beta, is change, is still the same formula, but this time around change in area divided by original area times temperature change or temperature rise. So that means your beta is giving us dA over A1 dt. Beta is A2 minus A1 all over A1 into bracket T2 minus T1. That's change in temperature. So that is your beta. Please take note of it. When they give you a question like this, when you input all these values, your beta, they will not give you the value of beta. They will give you the value of alpha. So you're expected to multiply that alpha by 2 to give you the beta. And that will be beta will be 2 times alpha. So if your alpha is 2.5 times 10 raised power minus 6, you just multiply it by 2, and that's 5.0 times 10 raised power minus 6. That will be your beta. That is area expansivity. Now, the third that we talk about is cubic expansivity. Cubic expansivity. Cubic expansivity is simply increase in volume. All right, increase in volume as a result of temperature rise, and the symbol is gamma. So that gamma, there's a relationship between gamma and your theta or your alpha. So your gamma is 3 of alpha. Gamma is 3 of alpha. All right. So if they give you, if you are asked to calculate, you need to first multiply your alpha by 3 to get your gamma. So what is the formula? Your gamma is change in volume over original volume times change in temperature. And that will be what? Gamma is equal to V dV over V1 dt, which is the same thing as gamma is equal to V2 minus V1 over V1 into bracket T2 minus T1. So these are the equations that you need to answer questions on expansivity. All right, so I wouldn't want this video to be too long. So I'm going to be doing the next video where I will talk about elasticity, tensile stress, tensile strain, Young modulus. I will also talk about electricity, and then we will go deeper and deeper into other. I will also be talking about optics. All right, I'll be talking about lens and mirror. I'll talk about magnetism. You don't want to miss the second part of this revision class. So thank you for being a part of this. If you have not subscribed to this channel, do well to subscribe right now and share with your friends. If you have gotten value from any topic from the topics I've listed, please go to this comment section and type the topic that was most helpful to you and type value there. Thank you so much. See you in the next class. Bye for now.